This is a thing called ChatGPT. I'm guessing a lot of you people know it and use it. And it's a chatbot that you can speak a heck ton of things to. There is also this other thing called Stable Diffusion. While not known as ChatGPT, it's still pretty renowned for its art generation capabilities. Neural networks are the fundamentals that make up these AIs. Well, before they remained as a little subfield of computer science, just as one of the many approaches to machine learning, or generally better known as artificial intelligence. Oh boy, was this idea not new, as they were originally developed in the 1950s. But ever since this guy, and, well, his company, paved way for the rapid surge in GPU compute power, it allowed the world to see, wait, neural networks can do this type of thing? Like in the case of AlphaGo, beating the best chess player in the world.
Congratulations to AlphaGo and to the entire team for a great match. And congratulations to Lee Sedol, who is a really impressive world champion.
Well, NVIDIA's stocks grew by a ton and made a lot of money in this AI stuff industry. Computer science is a relatively new field compared to others that have been around for hundreds or even thousands of years, like math and physics. But it's a rapidly evolving field. We first started out with huge machines operated manually by teams of people, then we eventually got a computer into an average person's home and gave it a pretty looking interactive screen, and got people connected across the world with the World Wide Web, and then phones, right? It's a crazy history with names all over the industry. And now we're at another computer revolution, AI. While we have shown some of the most heard of things that AI is known for, but there's still ongoing research into deeper and more complicated practical uses of them, like self-driving cars or protein folding. So now back to this class. What are we going to talk about? The big idea will be for you to understand the basics of neural networks. Then we will go into a little bit on natural language processing and end on the note of understanding GPT. There will be some math over the duration of these classes, and I will give some additional links that I strongly recommend watching/reading if you feel like you're not understanding what's going on. And we will go over the process of making a simple neural network, if I can find some online resource that doesn't require any coding experience, and also the process of training your own little chatbot based on an existing large language model. If we get any time, I'll write out an additional part discussing computer vision and eventually how AI art is made, but I'll need a little more research on the technical details as to not give you wrong information. Okay, so what is a neural network? While I want to use the equivalent to the hello world of deep learning, the MNIST classification examples throughout this first part of the course, I'll instead talk about college admissions, US in this case, given some student with a certain set of grades, extracurriculars, essays, SAT, letter of recommendation. Let's first get a conceptual idea. When we build algorithms to do something on a computer, it's usually a set of generalized instructions. Do this, then do that. If this happens, do this instead. But when faced with a question like this, we seem to fall short with what logic and math we have to write out for a direct, systematic solution. In a sense, there's a lot of things us humans can just do but can't explain well to a machine to do, like talking, walking, or drawing. Neural networks chuck all that deterministic logic out the window and say, well, what if I try to replicate these activities of a human? Start out like an amateur and improve my performance gradually over learning from experience, like how a human learns over time from his mistakes. As we've already seen a diagram of a simple neural network, we might raise some questions. What's the neural part with the neurons and stuff? And what's the network part with connections and interactions? Now, I'll try my best to tell a little story that introduces everybody in the show. So, welcome to the stage, Bob. He is an admissions officer at a university. And he reads tons of students' applications every day and determines if the student should be admitted to the school or not. And yes, Stardew Valley is a great game. So as usual for today's work, he started reading the application of a student. A student's application will be comprised of the 5 parts that I've already discussed. And for the sake of simplicity, we'll have them as numbers that range from 0 to 1, with 0 being terrible and 1 being excellent. Since we want everything to be on the same scale, apples to apples, and not oranges to apples. Bob, of course, doesn't treat all parts equally. He considers some factors more important than others. For example, he might believe grades and essays matter a lot, so they are given a high weighting. Extracurriculars and SAT scores, not so much, and so on. So he assigns each one of these parts a weight based on how important he thinks they are to admissions. So like 0.5 times 0.6 plus 0.8 times 1.4 plus 0.6 times 0.8 and so on, until we get the final score of 3.39. And this process makes sense, right? Multiplication gives the respective weight Bob wants for each part of the application, and the addition allows him to assess how strong a participant is overall, according to his principles. But of course, Bob isn't the only person on the admissions team. Meet the rest of the team: Alice, Carl, Dana, and Josh. Each of them, like Bob, has their own perspective on what makes a strong applicant. For instance, Alice might care more about grades and SAT scores. Carl focuses on extracurriculars and the letter of recommendation. Each admission officer reviews the application, applies their own weights, and comes up with a score based on their own perspective. They then pass their scores to the head of admissions, who gathers input from everybody on the team. But obviously, the head of admissions doesn't take everybody's score just at face value. They weigh each team member's score based on how much they trust their judgment on these different types of students. Perhaps Bob is relatively new to the team. He just joined last year, so his opinion doesn't hold a lot of weight in the eyes of the head of admissions in compared to Josh, who's been the leader of this team for a decade already. So it's just weights again. We go through the same process of adding and multiplying to get the final decision of the head of admissions, which can be that if the student's final score passes a certain threshold, they will let them in. In this case, I just used some random numbers for this example. Okay, but there is still something we haven't talked about yet: bias. Bias can be viewed as an instinctive favorism towards something, or a natural negative view. Like, Bob may be an admissions officer that tries to talk about the nice things of the student when he shares his opinion with the head of admissions. However, Alice is very keen on the student's application and believes they might boast upon themselves and make them sound like a stronger applicant for the sake of doing so. So she tries to prick out some of the things that are potentially negative about the student when sharing her opinion. This is regardless about which student is being viewed in the application process, and so we can say that there's innate bias in the admissions officers. And in this numbers game, this just refers to adding an additional number at the end of all the multiplying than adding, as this number isn't influenced by the applying student's portfolio. Now, let me ask you a question. What happens if the head of admissions decides that this voting process of admissions officers need to go through more layers? Like, instead of just this one team reporting to the head, they report first to another team and then another. I mean, I'm just duplicating them right now, but you understand the idea. You might be seeing a problem. Wouldn't the values at the later parts of the network be just getting larger and larger? Right now, I've only included positive weights, which isn't the real case for neural networks, but that is still a valid concern if our network grows bigger and bigger in layers. So what we can do is squish everything down to a designated range at every layer, normalizing the values that go through this network except the inputs and outputs. Like in this case, we'd like to squish all the values between 0 to 1 as it goes through our network. So we apply something called a sigmoid function at the end of all the addition and multiplication of weights after the addition of the bias. The function itself is a bit intimidating, but we don't have to go into the mathematical details right now. Just know given some input of a number, its output will be between 0 and 1. Large positive numbers go closer to 1, and smaller negative numbers will go closer to 0. More generally, these functions are what's called activation functions in the industry. They are crucial in neural networks as they give the network non-linearity. But that's something we'll discuss in detail a bit later. We only had 11 neurons in our little story with all of this admission stuff. But in reality, as AI grows more complex, they scale up in incredible magnitudes with millions and billions of neurons. And the action performed by each of those neurons may not be all so humanly understandable. Which is why there's this whole field dedicated to explainable AI. Researchers who are dedicated to explaining the underlying behaviors of what neural networks are actually doing under the hood to achieve their results, and maybe even gain true insight into how to create a systematic approach to a problem at hand. But back to this, now I need to formalize what I've explained throughout the story. Neurons are functions that depend on the previous layer's neurons, weights that are connected to it, and its own associated bias. For a single neuron, its mathematical definition can be summarized with this given diagram. And this would be it being fully written out for our first neuron in the hidden layer, Bob. While all the maths we've encountered today, except the activation functions, is basically just simple addition and multiplication. And every other neuron of this layer will also have a similar looking equation. Now, here's a roller coaster ride. As every neuron's formula is just a linear set of equations, we can write this in a vector matrix multiplication format, where all the values of the first layer become the vector A1, the weights become the matrix W1, the values of the second layer become A2, and the biases become B1. And so this is the equation for a linear layer in a neural network. Now, I know that might sound like a lot to take in suddenly, and sadly I really won't be able to teach you linear algebra in 2 seconds. So here's Grant Sanderson's animations on this. Hope it gives you some visual intuition of what I've just written. His variable names are a bit different from mine because he started from 0 instead of 1 for me. And he directly had the sigmoid function symbol on the outside instead of a general function, f, like me. We'll quickly discuss the dimensionality of these vectors and matrices. The input vector has dimensions 1, n. The weight matrix has dimensions n, m. The bias vector has dimensions 1, m. The output vector has dimensions 1, m. In the industry, we call this a linear layer in the neural network. Other alternative names are like feed-forward layer, multi-perceptron layer, all just the same thing. It's this formula here that we just discussed about. Well, you fully know how a neural network, at least the basic one, operates. We get a vector at the input layer, and it repeatedly goes through these linear layers until we reach the output layer. Don't mind that normalization thing in the image right now. And really, it's just a big voting system one round after another, like was that example of admissions I showed you. But that still leaves a lot of questions, like how does learning occur here? Or why the heck does this even work in the first place to solve these problems? Or wait, so what are the default values of these weights and biases? Slight spoiler, multivariable calculus. We'll formally write out how it all works in maths, but it's nothing difficult and you should be able to understand it.